Hello and welcome to the webinar on AnyLogic's Material Handling Library, Essential Techniques and Functionalities. My name is Arash Mahdavi and I'll be your host today. This is going to be part 2 to the webinar that we did a couple of months ago with the same title. Today, as our guest presenters, we are thrilled to have Tyler Wolf-Adam and Jeff Wertz with us. Aside from being a great simulation modeler, you probably know Tyler from previous webinars and the work he put into creating Python connectors for AnyLogic. And you probably remember Jeff from our previous webinar around AnyLogic Model Manager or AnyLogic Cloud. Okay, let's start by the agenda. I will start by briefly going over the part 1 of this webinar series to give you some ideas about what we covered and what you can look for in the first part. Then we get to reviewing several models. These models are from AnyLogic example models, how-to models, tutorials, and also we created one custom models. We are going to cover conveyor systems, cranes, storage systems, and transporters. And as you can guess, this is going to be more intermediate to advanced level models because we covered the basics in the first webinar. And at the end, the three of us will join you live to answer your questions. And we'll have time for reviewing other reference material. As part of the follow-up material that you receive after the webinar, you will get access to the video recording, all the models, and any question that was not answered in the Q&A section. So without further ado, let's start the webinar. Let's briefly review what we covered in the first webinar. If you go to anylogic.com, resources, videos, you get to this place that have all the previous webinars and other educational videos. And here you will find the part 1 of this webinar series. The other way around would be to go into our YouTube channel and find a video there. Okay, let's briefly review what we covered in the first webinar. In that, I started by very high-level overview of material handling library, and then we went straight into conveyor system. We reviewed several models like conveyor, enter, exit, pallet packing line, reversible conveyor buffer, and then Tyler started to show us models that were around transporter systems like MoveByTransporter, SeizeTransporter and ReleaseTransporter, transporters moving in free space. And then at the end, I showed you some reference materials for you to learn more about the library. So I highly recommend you to go and check out that part 1 because the examples that you were going to see in this webinar are follow-ups to what we covered there. We are not going to repeat ourselves. The models that you will see here are going to be more advanced. Okay, so let's start by looking at the first model. As a first model, let's start by reviewing this conveyor offset model. So there are some items that are coming from the source, and then they will go into this conveyor. What you see here is a couple of things that happened. So these items actually ended up being at a specific location. They are all not all went to the end of the conveyor. Each one had a different destination when it gets there. And they didn't leave the conveyor either as well, right? So they are waiting here. Okay, what we want to happen is if I click on any of these cartons, I want this worker to come in, pick it up, and put it on the exact same location, like perpendicular to where it is right now on the other conveyor, and then the conveying should happen there. So let's click on this. So it picks it up, puts it at that same location, and it starts moving toward the end. Let's pick this one, and so on and so forth. You see that we can actually manually pinpoint the one that we want to move, and it happens. So let's see how this is being done. There are many things that are happening here. I'm just going to look into specific things that I think would add some value in this case. First, the process of bringing these cartons and put them on this conveyor, which is called processing conveyor. This is the processing conveyor, and this is the exit conveyor. But I don't want all of these cartons to go to the end of the conveyor. I want them to just stop along the way with some gaps. So how can I do that? So these two are, again, creating the items or cartons, logical queue, and this is the convey block that says convey from this conveyor, this entry conveyor here from here, and then move them to the target conveyor, which is this processing conveyor, to the end of that. But we also have some offset, okay? Offset from the end of that conveyor. So what that means is we can use this value to actually arrange them the way we want it. But the offset of each carton to the end would be different from the other one. So we cannot just say 5, let's say 1 meter, they're all going to be stacked up on top of each other or trying to get close to that at the same location, which is not what I wanted. I want them to have different offsets. Maybe the first one has 1 meter, 2 meter, 3 meter, and so on. So this is what we wanted. So we are going to use a function that calculates the proper positioning of these cartons. And here you see that I can pass the agent or the item that is coming in and pass it to this custom function. What is this custom function? Get processing line offset, or get process line offset. So let's click on it and see what's going on here. So again, can think more about this formula, but based on the ID of each agent that is coming in, we're going to multiply that by this value, which is basically the length of each agent plus the gap that it has on that conveyor, the gap on this conveyor. And the gap here, this API is pointing to this, right? This value. So we add that together. Let's say the length of the conveyor and the gap is 2 meters. So based on the ID, it's going to be 1, 2, 3, 0, 1, 2, 3. And then we have, different offsets based on the ID of each carton. And that's how they are put on the same conveyor. So let's kind of look at it once again, see how it works. So they're all coming in and they all have different offsets. This is the 0 ID. So it has 0 offset and 1, 2 multiplied by that length plus gap. So they are now positioned the way we wanted it. Right after that, we have a delay, but this delay, if you look at it, it says it's not actually have a specific time. It's going to be kind of forever until the stop delay function is called. It's manually being called. So how that's happening is based on clicking on the box. And how that gets triggered is because we wanted to click on the box, it should be on the carton icon itself, right? So if I go inside the carton, look into onClick, you see that here it says when somebody clicks on that icon, go to main, find this processing, which is the delay, and stop delay and release or stop this or release this carton from that block, which makes that agent to leave the processing time and the rest of the process happens. Okay, so let's again see what I was talking about. Here we have this. They're all coming in. They're all here. If I click on it, this one is released and it continues in the process. So let's see what happens when I click on a carton and it goes to the next block. First, it's gonna attempt to seize this worker, which I click on the worker, you see that it's gonna be the home location of this is here. And at this point, we want this item, the carton, to exit from the network that it's currently at, because we wanted to move it on kind of this empty space, which is not part of the conveyor system, right? We say exit, and then we use the generic move to block to move it from here to here. But just to make sure that it kind of uses the same kind of coordinates, we say the x-axis or x value would be the same as before. For the y coordinate, go and get the exit conveyor a start point, and you know that it has a y coordinate, and add a little bit to it, a few pixels, so it goes to the kind of the middle of this conveyor. And then we have a logical queue, and here, when this item is moved by this worker to this part, we again are going to say, using an enter block, we're going to put it back on the conveyor network. Here we are going to use this offset feature again. We wanted to put it on this, but not exactly at the beginning or end of the conveyor. We wanted to put it at a specific location. Here we're going to say an offset from the beginning of this and of this exit conveyor. And we are using the second function just to calculate the proper location that it has to be. Again, looking into this function, it says get main line offset. Let's see what we have here. Finds the agent x-axis, its current location. And then it says if we kind of subtract the coordinate of the beginning of this conveyor, then we only kind of need the distance from here to here. So we say all the coordinate up to this point, the coordinate to the x value to this minus this, it becomes just the gap or the offset between the item at the beginning of the conveyor. And we scale it to make sure it's kind of matches with the scale of the model that we set here, and we put it here. So it will show up in this location when we say this. With the offset, it will show up exactly on the conveyor, but at the same location as it kind of a perpendicular to where it was before it left the other conveyor. And then we move them to the end of this conveyor, right? So let's take a look into it once again to see what's going on. These items are coming in, we click, gets it, puts it with the correct offset on the exit conveyor, and now it is moving to the other one. So we have 4 boxes or cartons in this. Let's release one more. So it released, picks it up. Now it's on this, moving toward the end. So explore it a little bit more and you get the idea. What we wanted to show here was the offset feature so that you can actually arrange items on the conveyor exactly at the position, or convey them to the exact position that you want, or put them on a conveyor in the exact position as you want. The next model that we wanted to look at is called Reversible Conveyors. This is a new feature that is added to the MHL and was highly requested. So this model, compared to the other ones that I showed so far, is more advanced. So it uses more techniques here. So don't get confused. If you're not familiar with what I'm going to say, don't worry about it. The main thing that I wanted to cover is this reversible conveyor feature. So that's the main purpose, but there are other techniques that are being used here. Okay, so let's take a look at this model and see what is going on. So there are some items that are coming in. The ones that haven't been processed are labeled blue. So the color is blue. And these are stations, when they are not occupied or kind of cease to be used, they have this green indicator. If it is assigned to a specific box or item, it will turn to red. So this one is now going toward this station. So this is going to be red. So this is moving toward that. And as you can see, the next one that comes in is going to take the next one and goes there, and so on and so forth. And when an item is done, let me pause it. So this one that was done in the station, you see that the direction of this conveyor is reversed. So it went this way to get to the station, but now it's coming back. And the color is changed to red, meaning that it's been processed. So it's ready to leave here. But if I keep running the model, so there will be some situations like this, that there are more items coming in than what can be processed right away. So there is no chance for some of them as they pass through this to actually get to any of these stations. So these ones that hasn't been processed, they will go back and they attempt again to be assigned to a available conveyor. So that's the mechanics that we wanted to achieve. So they're all coming in, they try to get to the closest station if it's not occupied. If not, they go to the next. They have three basically chances. If all of them are occupied, they go back and attempt again. And the part that is we are using reversible conveyors are these sections, in these three sections between the stations and these tables. Okay, looking into this, you see that each of these conveyors by default has an arrow on it, which shows us the direction, the default or forward direction of conveyor. And if I click on it, you see that the reversible checkbox is not checked. But for these ones that have these two arrows, it is checked, meaning that it can reverse its direction. But these reversible sections can have default forward direction. So if I uncheck this, I can see the default is this. So that's good to know because we're going to use that default at some point. So let's see what's happening. There are three sections that are put inside this population called magistral conveyor. So you see it's an array of conveyor paths, and these three sections are added to this collection. And then we have a collection of these three conveyor sections. And then we have these three nodes added to this collection, okay? So why we are doing this? So first, we created this and we made a bundle of similar components in these collections. Why we wanted to do it? Because I want to create a specific object that is a combination of this, this, and this. This would be one thing, which would be the path toward the station and going back. And then the second one would be this plus this and this. And the third one would be this plus this and this. How can I do it? First, I need to, this is what we did. We put them similar sections inside these collections. Then we create a custom agent. We call it site station. And site the station is that object that knows its magistral conveyor, station conveyor, and station node. So each of these objects will represent one of these three things. So the first one would be this, this, and this. The second one would be this, this, and this. And the third one would be these three objects. It also has another variable called occupied, which is a Boolean, and it tells us if that specific three section object is occupied or is being used or not. So how I can make that population, you create that agent type that I just showed. These are all parameterized and each, of the correct type. And we have a Boolean that represents this being occupied or not. We create a population of this side stations. We said we are going to have three of them. We know that there are only three. And for each one of them, when AnyLogic runs and initialize the model, it's going to get into these collections and pick one of these elements and associate it to one of these objects. And the trick that we use is we say, okay, index, so that which is the index of the replicated object in this population. The first one is going to be 0, 0, 0. It gets element 0, 0, 0 here and puts in the first object. The second one would be 1, 1, 1, and it creates the second object, and so on and so forth. So let's run the model just to kind of see how that works. So regardless of what the model does, first, all of these objects will be inside these collections. And then we also have this 3 side stations, 1, 2, 3. And for example, if I double click here and see what's going on, the first one has the, all of these elements. And I can actually, if you want to, you can go to the second one and the third one. So they're all kind of modeled like this. So now I created this custom object that knows all of its inner elements, these 3 elements. So this newly created custom combination of objects could be used easily inside this, and it helps us to manage the assignment of a station to an item in a more controlled way. Okay, the first thing that is happening is the item is coming in from the source. It enters this network. The network is this, right? And now we want this new item that came in to pick the first station. How can we do it? Inside the item, that assignment happens. So it's the local thing that happens inside each of these items. So I need to go inside the item. There are 2 things there. There is a target station, which is one of those side stations that we created. Side station is these objects that we created from the other space markups, right? We say when an item comes in, go and pick the first side station. Pick this one by default. All of them that are coming in are going to pick this, right? Okay, but we know that's not going to be feasible. So we need another function that calls reevaluate that selection. It says has a logic that says if you reach the 3, go back to the first station. If you are not in this, you are not at the end of your options, then try to go, if you're in 0, go to 1. If you're in 1, try to go to 2. This is like what it does. It tries to select the next possible option. So that's the reevaluation. This doesn't mean that the next one would be available. It's an attempt in testing the next one. Basically, just imagine that we have a circle. We're just looking into the next option with this reevaluation function. So that item that entered this network from here is going to be using this conveyor block, and it will be conveyed to this specific magistral conveyor. It says from the one that you currently selected, the target station that you selected, by default, it's going to be the first station. Try to go to that magistral conveyor, which got to be this, right? Then it tries to look and see if its current selection, for all of them, their first selection is going to be the first station. It says, check to see if that station is occupied. Occupied is this variable inside each of these objects, right? We check that and say, if it's not occupied, then you can continue. And like, let's say we selected this, it's not occupied. Now we go to the next. It says, okay, now you can go to the next, this target conveyor is going to be the station conveyor, which is this. And then it moves toward this station node in that object, which is this. And then it waits there for the processing time and the rest. So I'll get back to this. But the point is here at the beginning, because all of these items are going to select this, there is a chance that when we say go to this and it's here and it gets to the evaluation, it hits a wall. And this is the first choice, which is this is block. So what happens? We say, okay, try to reevaluate, which means that now move and evaluate this one. So it goes back and attempts to do the same thing for this. If it's, again, is occupied, it goes to this and so on and so forth. And as this is happening, let's say we check this, it was occupied, this was occupied, was occupied. You see that this evaluation is keep moving us to the next, and it takes us back to index 0. So we get to this point, so we are kind of here, and it says go back to index 0, which is this one, the magistral conveyor section of the first object, which is this, so which in turn basically means that you need to take the loop back to the beginning. Now that we kind of saw some side techniques, let's get back to our main topic, which was the reversible conveyors. So let's see what is happening here. The first thing is when the object is coming in, it goes up and it gets to this station, which is fine because the default was activated in that direction and everything was going to work fine. When we are done with the process inside the station, we need to reverse the section. How we do it? We do it in the process block, which says on at exit when the process is done, change the color of this icon. That's a kind of an indicator, but this is what we are doing. We say change the associated station conveyor, which is this or this or this, depending on which station we are at, change the direction of that after you're done processing so that the process item now can move downward or kind of in the opposite direction to the rest of the conveyor, right? So that's the first one, but this is not enough because for the next one that are coming in, this will be in the opposite direction of what it needs to be. So we need to fix it. After this item leaves here, we need to make sure that it goes back to its default and it's ready for the next ones to come. So if you click on any of these things, you see all three of them have this kind of back to default API call as well, and says when the trailing edge of the box hits the end of this conveyor section, you should reset yourself or change your direction back to being forward, which is going to be up. Then that would be ready for the next ones to come. So again, by default, it's going to be up when the item comes in and gets to the station and it's done in the processing delay. We are going to set it to be like this, downward. And when the item leaves this section, it reaches here, we are going to reset this section direction to be forward looking or upwards in this case. So that's the technique. And again, running it once to see how it works, you see all of these things in action. So these boxes are coming in, they go up and down. You see they can move in both directions, and you can see, you know, how this sections change direction to be reversible. Let's continue with the next model.
The next model we will be discussing is the MoveByCrane model. In this model, we'll be reviewing a specialized space markup object that is specific to the material handling library referred to as a crane. Now, this crane, I can drag and drop just like any other space markup item. And I'm able to edit its size, some of its shape, position, initial position of the crane. And I can also specify things such as its speed, specifically its trolley speed, lifting speed, and the jib rotation speed. And the movements at which this occurs can be specified step by step or concurrent, such that all pieces of a crane will move simultaneously under concurrent, or all movements will be, as the name suggests, step by step. I can also change things such as appearance. Here, I can set the type of crane I would like to see: an industrial jib crane, cathead tower crane, or a flat top tower crane. Let's take a look at what makes this space markup item rather unique. So here we're going to associate this jib crane that we've added, that we've set up all of its speed, we've set it to be an obstacle, and we've even added a block zone. What this block zone is, it makes sure that no movements or turn will occur in this specified zone that I can either specify by angle or just by changing the shape itself. Here in this model, we have these specified blocks called MoveByCrane. What this block allows you to do is seize and release a specified crane. Now, what makes this crane rather unique is we are seizing the actual space markup item as opposed to a resource block or a transporter fleet block. And as you can see, all within inside of this block, we're going to seize and release it. And what we have added as well is we have specified the agent selection pattern. And what we've done here is we've changed it from first in, first out to a custom and assigned a custom pattern integer to it. Now, if I examine each of these MoveByCrane blocks, they all have an assigned custom pattern value. What this means is when an agent enters these blocks, they will attempt to seize this space markup item, and the order at which they will be seized will be dependent on this custom pattern. So let's actually take a look at this model running. So here you can see agents enter on a conveyor belt. And the first step as they go through the system is to be unloaded from the conveyor and loaded into this tank. Once they are done, they will be loaded onto the second station here. Once that process is the station has finished, the crane will be brought back to place the item from the station to the conveyor belt. And you may notice from this behavior that what we have done is made sure to prioritize the throughput at the end of the system, such that any items that have left the processing station take priority over any of the other MoveByCrane operations. In here, we can see a 3D visualization of all of the crane movements. If I slow down the model a little bit, you will now notice that each of the movements are adhering to the step-by-step rule that we set up for the space markup item. If I go back to the model properties, let's select that crane, and let's take a look at what the other types look like. In this case, changing its appearance really only changes the animation. You won't be changing any internal logic to this space markup item, only what it looks like. So in this example model, we'll be taking a look at the SeizeCrane and ReleaseCrane. Here, we have added the specialized space markup item, an overhead crane. Just like any other space markup item, you can drag and drop this into your model and specify any of its properties that you need to. This can include number of bridges, components movement mode, whether it be step-by-step, concurrent, or as an independent hoist. You can also specify other things such as the bridge, trolley, and hoist speeds, as well as any acceleration and deceleration that you'd like to specify. In this logic block, I've added a SeizeCrane. It works very similar to other Seize blocks, whether it be Seize Transporter, Seize Resource. In this case, we are seizing the space markup item, the overhead crane that we have added. In here, what we have done is specified its destination. The agent selection pattern will be first in, first out, and a safe height for the item to be picked up. Let's actually run the model. The purpose of this model is the different steps that it takes to build these engine blocks. They start off as these raw blocks that have to be loaded into separate stations to go through different steps of the process. The entire time, we want the crane to be seized or essentially stay with the engine block as it goes through the system. So if we look back at the logic, we notice here that we initially will seize a crane. Different operations may occur, represented as a service block and a delay block. And before we even release the crane, we may have some movements to specified stations. If I take a look at this block to station, which is a MoveByCrane block, I have unchecked the SeizeCrane and ReleaseCrane options. This allows for other steps to occur and other movements to other positions to occur before we eventually release the crane. And one thing to take notice here is instead of releasing the crane right after we're done at this station and we've joined the part, what we want to do is add operators for either the loading to crane or detaching from the crane. Once the crane has been released, we could specify where it'll hook to, where the hook will go. In this case, we're going to have it return to its initial position if there are no other tasks available. And here in these different MoveByCrane blocks, you can also notice the different functionalities for destinations utilized. Here we can specify different specific nodes, maybe a specific position on conveyor, or in this case, the destination is going to be the agent that has actually seized this crane. In this example model, we're going to take a look at a crane system with multiple bridges. Here, we have added an overhead crane object that has two bridges, which their component movement mode is set up to be step by step. And we have specified the hoist speed and left the default trolley and bridge speed. What we have done with this crane system is implemented two specific handling options. We can have container selection be done by the whole system, where the nearest crane bridge will be selected to handle the container, or we can specify which bridge will choose which container depending on its color. Let's take a look at the whole system first. So here we have a pile of containers that each of them have an integer value assigned to them. And in this case, we want to unload these containers based on the highest integer. Whichever container has the highest number will be selected next to be unloaded. After a certain number of containers have been loaded onto a train, the train will leave the system. In here, let's take a look at the logic. You'll notice how we have two separated big sections of logic, labeled transportation by whole crane system and transportation by individual bridges. When we started the model, we chose the first value of this radio button, which will determine the remaining logic for the rest of this model. If we want to take a look at transportation by individual bridges, let's stop it for a moment, select the other option, and now we'll notice that all of the containers have not only been assigned an integer, but a color as well. And here you will notice that the two cranes will essentially work together to make room for one another to achieve each of their specified goals, which is picking up the next highest integer container and delivering it to a trolley for delivery. Here you will now notice that the lower transportation by individual bridges is now selected. Because logically, what is occurring here when we choose this option is first we want to check the type of container. Is it blue? Yes. Then we want to move by the blue bridge. Is it not? Then we assume that it's red, and hence we want it to be moved by the red bridge. In this model, we utilize the MoveByCrane blocks for the actual movements. Here we have specified destination is XYZ. We have seized the crane, but we have not released the crane yet. Because first we want to pick up the crane and deliver it to its destination, which is going to be the nearest load point. But before we have let that crane go, we need to find the nearest AGV and seize it. Once that AGV has been seized and has arrived at the load point, now we would like to use our seized crane to deliver the container to its selected load point. And then we'll be releasing it and delivering the box to its specified load point and releasing our AGV. One last thing I'd like to bring up about this model that some of you may be asking is what occurs when these two cranes are in conflict with one another. In this case, this is automatically resolved with the crane object itself, where first it'll be based on a priority of which of these containers is supposed to be picked up first, and a combination of what is closer. The next model we will be discussing is our job shop model. This is an example model that can be built by you using one of our tutorials. If you go to Help, AnyLogic Help, navigate to Tutorials, you will find Job Shop under the Process Modeling Library right at the top. So if you're interested in looking further or building this model yourself, please check out and take a look at this tutorial. Once again, found at AnyLogic Help and Tutorials. In this model, we'll be utilizing the storage object that can be found in the space markup items of the Material Handling Library. This storage object can behave similar to a pallet rack, where we can identify the number of racks, bays, cells per slot, number of shelves, shelf height, and even rack placement itself, whether it be standalone or back-to-back. We can also change things such as the rack type, whether it be selective or drive-in. For this example, we'll be sticking with the selective. One thing to note with this storage object is that we could define the number of racks either explicitly through these properties, or it could be calculated based on dimensions. And the same could be done for the number of bays as well. So now the size is all going to be dependent on how I draw the space markup items and the scale at which I have set up for the model. Now that we have a storage object set up, let's take a look at this unique block that comes with it: store and retrieve. When pallets are first injected into the system, the first thing we want to do is have forklifts, which are modeled as a resource unit via resource pool, be seized by this store block and have these pallets put away in this specified storage area. After a certain amount of time has passed, eventually these items will be seizing a CNC machine. Then we will be retrieving that specified item that enters this block from the storage object. And we have to find the movements by these resources. And here we have specified by resources, specify the resource pool, and a destination, which in this case is our seized CNC machine. So let's take a look at this running model. Here we will see a truck arrive. Immediately, forklifts will be sent to pick pallets off the truck and deliver them via the store block straight into the storage system. And here we can now see a 3D view of the shelves, the bays, and the number of racks. And after a certain amount of time has passed, you will see that these forklifts will be delivering these pallets to and from the CNC machines to the storage area. And let's take one more look at that store block. Inside of the store block, we do have other options for how these agents get put away inside the storage area. In this case, as discussed, we have to find these forklift agents and assign them to put away all of the objects. Now, the speed at which these things get put away and travel to is going to be dependent on the properties specified inside this resource pool. And inside of the store object itself, we can specify the elevation speed. So we do not define the elevation speed by a delay, but as the distance defined by the speeds set here. But in the store block, we do have other options. We can specify by transporters. And if we add a transporter fleet, we can specify them. Or in some cases, we might want them to be put away independently. So in this model, we're going to take a look at the different slotting policies for storage. Here, we have added a bunch of pallets that will be put away in the blue storage. In this case, we're going to have the forklifts put away these objects in a random available cell. If I speed up the model, let's take a look now at the red storage, where here we have to find inside of each of these pallets a specified property that essentially defers to a specific row that these objects have to be placed in. As you could see by the option selected of drive-in for each of these storage objects, the forklifts can actually enter and stack these pallets accordingly. Now let's take a look at the green storage area. Here, items will be placed in the storage area consecutively from the backmost corner area to the topmost corner area. Here you will see items that are stacked from the furthest row in the furthest corner and filled up consecutively, stacking on top of each other until this is full, and then on to the next row. In this example model, we're going to be taking a look at an automatic storage retrieval system as it's modeled in AnyLogic using the Material Handling Library. To simulate this type of system, I'm using a system of conveyors with a convey block, a storage object with its corresponding store and retrieve blocks, and how items will actually be put away and retrieved from said storage will be all done through this transporter fleet. And some things to take note of that is very specific to this model is we have created this custom block referred to as ASRS assignment. What this block does is when agents first enter the system, before they even enter the conveyor system, we want to assign a specified storage slot inside of the storage object and reserve it for this incoming agent. And what this allows us to do is if we actually look inside the agent, we could see we are saving things such as the conveyor we'll be using, the bay number, rack number, shelf number, and aisle number of our corresponding reserved storage slot. And how this is accomplished, if I go back to the ASRS assignment block, is with the use of this function, assign storage slot, where we'll be passing in the agent that is moving through this block. And if we actually take a look at this model function, what it is doing is first we're initializing a variable to reference a storage cell, and then we'll be using this do while function loop to keep searching for a random free cell inside the storage. And we're going to keep doing this while we don't have one available. After we found one that is available, we're going to set the reservation based on this storage cells, rack number, bay number, shelf number, and the agent that is reserving it. From there, we want to save the location of this reserve cell inside of the agent that will be referenced inside the store block. And the last part we need to do is based on the reserve cell storage cell, we want to save the respective conveyor path such that an item will be delivered to the proper ASRS crane system, such that this agent will be delivered to its respective conveyor system that is closest to its storage cell. In here, before we go into the running model, let's take a look at where some of those assignments are utilized and referenced. So first, inside the convey block, we will be entering here in the system, but the destination or the convey to is going to depend on the aisle number of this agent's reserve cell. Now, when an agent enters the store block, we are going to specify the transporter fleet ASRS, which there will be one for each lane. And here, we are having a slotting policy according to a specified slot. Whenever an agent enters this block, we will be referencing the storage object and we'll be getting the slot based on the rack number, bay number, and shelf number that this agent has reserved. The last step of this block is we're going to need to customize our transporter choice. Because we will have a transporter for each individual aisle found in the model, we want to make sure that when he arrives at a specified conveyor, he's using his respective or correct transporter fleet. And how we do this is we have added our transporter fleet agents, these ASRS vehicles, to a custom agent population where each of them has been assigned an index that corresponds to their position. In this case, lane 1 corresponds to index 0, and so on and so forth. This enables us to make sure that when agent enters this block, he is only picking the ASRS vehicle that is inside of his aisle. Now let's actually take a look at this model running. Here we can see the system running in a 3D view. And as mentioned, we will have pallets entering the single conveyor belt. And dependent on their internal destination, they'll be routed to a specified conveyor. Once they have reached the end of it, they will be loaded on to this ASRS vehicle, which will take them as close as they can to their slot, then hoist them all up until they're at the right level and slide them on in. Now, all of these movements and the speed of which they occur is going to be defined through things like the elevation speed found inside the store block, as well as the loading time. And similar to that, we can also specify inside of the retrieve block, once again, the transporters will be utilizing their unloading time, their destination, which similar to how it enters the model, we have a collection of exit conveyors that correspond with this agent's aisle number in their specified storage, and they will be brought to a specific conveyor depending on that aisle. And here we have also maintained that we are choosing the correct vehicle dependent on the aisle we are located in. And so as we can see, after a certain amount of time has passed, these pallets will be retrieved and sent to the outbound conveyor system.
So here we have the palletizing system with AGV model. And this is a very complex model, and I won't be getting into the details of it, but it's an ideal example to see how a system can come together when it combines many useful aspects of not only the material handling library, but also AnyLogic features in general. So if I go ahead and run this to show the operation occurring. So in this model, we have a combination of conveyors delivering some product, which there's some complex batching features, a complex batching operation that happens, including different layers that are separated by different panels. And once a pallet is complete, it requests an AGV to come pick it up and deliver it to some outgoing conveyor. And as you can see, when they kind of come through this congestion point, there's again some complex routing that's going on, and bottleneck detection and handling automatically, which if you want, you can customize that through the provided blocks. And as these different cranes run out of resources, the AGVs will also be used to restock the cranes with more items. And there's a logic and statistics tab if you wanted to play around with the sim and flight mode or examine various different statistics. Some interesting remarks about this model is that static elements like this restock area are defined on main or our global environment. And these are elements that aren't going to change at all. So I can click on this conveyor and see its properties, same with these various different paths and nodes. Now, more complex areas which may need to be replicated are containerized. For example, this palletizing cell. So when I select it, you can see that the bounding box is around this whole section of the space markup. And based on the naming scheme, you can see that it's just the animation for the palletizing cell agent. So if I double click to see inside of that, you can actually see that there's a combination of different space markup elements, even including the network port, the cranes, the conveyors, the different paths and nodes, in addition to this serving as a custom block, which is used as part of the logic that's defined within main. So in this way, the complex logic is containerized within a block, which makes for a much more clean and organized interface in defining our logic. So similar to how you see with traditional or built-in AnyLogic blocks, you can set up element selectors for these custom blocks, their parameters, and so you can make for a lot of flexible logic. And in this way, you can build your model assets as flexible puzzle pieces for all complex testing and analysis. And so because of the way that this is built, if we wanted to later test, like what happens if there's a fourth palletizing cell with the crane in this whole operation, all the logic that's embedded within that, it could just be as simple as taking this, the AGV section, just shifting it over to the right, and then going back to our population of custom palletizing cells and incrementing this 3 to a 4. And as part of all of this, you can always containerize all of this into a custom library, which you can then add back into your palette so that you can use it in any future models as well, or distribute it to colleagues so that they can use it in their models. So in short, this palletizing system with AGV models makes use of many different components of the material handling library, including the path-guided transporters that you can use as a reference for all the possibilities in your own models. Now, next, we're going to be taking a look at this transporter control overtaking model. And I think the best way to explain it is to run it first. So if I go ahead and run the model and then I immediately pause it, I'll switch over to the 2D view. So in this model, there are items that come in at the start of this conveyor and have to move through a sequence of different stations. And each station has some inventory. And whenever an item moves in and starts the operation on that conveyor, it consumes one of the parts that this station offers. And you could think of this like a production line in which an item from this is being deposited in this package as it's moving through. So it moves through each of these stations and then exits the system afterwards. And so if I press play now, once this item moves to the end, you can see that it decrements that station's inventory by 1. And there's a refilling operation or a refilling policy that's in the model where once it falls below a certain threshold, a new shipment of parts comes in and it uses the AGVs to pick up that shipment and then deliver it to that station to refill it. And as part of that, it just so happens that the area needed to refill the operation, that is these areas in front of each of the stations, is also the quickest route to get from the start to any given station. So without any customizable logic, what will happen is that each AGV will be stuck behind another one as it's refilling any given station. And so as you'll see as I run this model, if I were to switch to the 3D view, once it gets to that station, it will block that path, allowing the other AGVs to overtake it and allowing maybe something that will emulate the real world operation much more closely. And so in the model, to be able to recreate this type of behavior, there's another lane that's added. And what we want to happen is that when an AGV goes to, enters on this path, it blocks it so that no other AGVs that are behind it can try to, they will be rerouted down to this overtaking lane. As part of the route calculation to take the shortest route, it will naturally find its way back to the fastest lane, and then it will continue along the path. So with path-guided transporters, it allows you to have custom routing logic, such as including or avoiding certain areas or paths. And you can do this in either the transporter fleet block itself, and there's a section here, if I scroll down, for custom routing. But there's also the same features and functionalities available in this block transporter control. The difference here is depending on the scope that you want this logic to apply to. So if you wanted to apply to all transporter fleets that you have in the model, you could use this transporter control block. But if you just wanted to apply to one specific fleet of AGVs, like if you have different types, you can specify it in here. And like I was saying, if I enable this, it has all of the same options as this transporter control block does. So within the logic, as the AGV goes to enter on the path, if it's currently planning on delivering to that station, it generates this dynamic event, which adds that, and this dynamic event is added as part of the model logic. It adds it to a collection of block paths. And whenever an AGV goes to make a route from one location to another, it consults the logic that you define here to do things like avoiding certain paths, like the ones that are contained within the blocked paths collection. And this checking against the certain paths to avoid or to include even, that happens either when it goes to make a new route, or it could be forcibly recalculated at any point that you might want. There's also some controls that are designated to certain space markups, like designating the speed limit or limiting the number of transporters. That isn't in this model, but you can see that in other example models. So since the transporter control block is used to customize the route planning and not the actual underlying model logic itself, what we could do is we can actually ignore it completely, which will disable all of this customization that we've added, so that we can try running the model to see how it performs without this customization. So now when one AGV goes to deliver that set of parts, all the other ones which are trying to go to their own station or to exit now have to wait, similar to how boarding an airplane works. So in summary, the essence of this model is being able to show how you can take a behavior that's out of the box and customize it so that you can more closely match the type of operations that you'll see in real operations.